Hi everyone, I'm Jaisidh. I'm currently a master's student studying machine learning at the University of Tübingen in Germany. I did a short stint as a research assistant at Ellis Institute Tübingen with Dr. Antonio Oviedo. And this is the result of that research. It's our ENLP paper called Almost Free Modality Stitching of Foundation Models. And I'm excited to be talking about it with you guys. So the main motivation of our work is the growth of open source pre-trained model releases, right? So as you know, pre-trained models release almost on a weekly basis right now, especially across language. In this plot, we just have a few authors. That's the main labs like Cohere, Eliezer, Quen, Google, Meta, Microsoft. And the number of releases that they're making has increased over the years. As you can see now, we have more options than ever. Just for those few labs that I showed in the previous slide, the cumulative Hugging Face repository release has gone up since the past 3 years, right? It's virtually um, paralleled that of TIM, and that's a big thing because TIM is just managed by a few people, and TIM is a repository of image models or image encoders or classifiers, if you would, and that's also gone up rapidly. So we don't really expect to see a decline in the number of options that we have in terms of pre-trained models that we have at our behest to use. And the cool thing about these things is that the usage of these pre-trained models is not limited to the modalities that they were trained on. So when we say uni-modal, it means that it implies like an image classifier because it was trained on a specific modality. It operates on a specific modality, that is images. Something like an LLM would also be a uni-modal model because it also operates on one modality, that is text. So as these models release, we find that they're being incorporated in increasingly multimodal systems, right? They act as modality-specific modules in multimodal systems like CLIP, for example, where you have a text encoder which is unimodal, an image encoder which is unimodal, but they share their representation spaces, and that's what leads to the rich foundational knowledge that we have at our disposal now. In SAM, there's a similar thing. There's an image encoder and a prompt encoder, which both feed into a lightweight mask decoder. Similarly, in Lava, you have a unimodal language model, a unimodal vision encoder, and the representations of these two models are fused via a projection or a connector. And the fused representations across the two modalities are used by the multimodal system towards a multimodal objective. So the cool thing is that we have a lot of options for unimodal pre-trained systems, pre-trained models to plug into multimodal systems. Now, the point of using unimodal models is to not train from scratch, right? It's to save compute and to leverage systems which already have a lot of rich knowledge contained in them. But you can't directly use a unimodal model in a multimodal system without some sort of fusion, without some sort of representation fusion that would guide the multimodal objective. This is what we mean by stitching, right? Stitching aligns features from pre-trained models using specialized trainable networks called connectors. So in CLIP, what one would do is slap on a small MLP on top of the text encoder, which would project the text embeddings to the same space of the image embeddings. And then we would train only the connector with the info and C loss. In MLLMs, we would use a connector on top of the image encoder and then project patch-wise features into the LLM's embedding space, and then train only the connector on the language modeling loss. So connectors are really what stitch representations, and they are the only trainable modules in the very first stage of developing a multimodal system. Of course, fine-tuning comes later, and that will become the basis of our work. So again, it's very nice to have a lot of options, but there are so many, right? And a few things that we know is that unimodal representation quality directly affects multimodal performance. And since we have so many choices, ablating the choice of each unimodal model will scale experimentation costs. So for example, in CLIP, if you have 4 image encoders and 7 text encoders, that leads to 27 pairs of models that you don't really know how they'll perform, right? So the question now becomes, how do we choose these uni-modal backbones from the perspective of a practitioner? Let's think about a simple heuristic. The image encoder that performs the best and the text encoder that performs the best. If we stitch these two, they will probably give us the best multimodal model, that is clip, a clip-like model. So in this plot, if you can see, if we take E2L, that's the best image encoder, and stitch it with ROL, E2L means Eva too large, and ROL means Roberta large. And if you stitch these two, turns out you don't get the best multimodal performance. You get the best multimodal performance with DEIT3 large and MPNet base. So this sort of tells us that we can't have simple heuristics or ideas like performance or parametric count and then predict multimodal performance. This actually requires search. So ideally, what we would do is, given n models of modality 1 and m models of modality 2, we would train n times m connectors between them that we call grid search. We basically train the full cross product space and find the best performing unimodal pair, right? And that would essentially be the best initialization point of our multimodal system. And now we can fine tune. But this is really unfeasible. If you know, multimodal image caption data sets are immense, right? Lion is 5 billion images, RedCaps is 12 million, YFCC is 100 million, conceptual captions is also 12 million. So if you now use such large data sets and then multiply them by n times m, because you have n models of modality 1, m models of modality 2, this cost that you incur via grid search on your modality specific models, it becomes computationally unfeasible, right? What we want from a practitioner's perspective is the best bang for our buck. So if we have a lot of options for each image and text model, we ideally want to search very cheaply and very accurately for the best pair. And then we want to fine tune as much as desired, right? From a practitioner, we sort of have a flop budget, and we don't want to finish the larger part of our flops budget on just searching for the best pair. We want to search it fast and accurately, and then fine tune to end up with the best model for our specific application, right? So this is the motivation of our paper. We make search cheap and accurate. And the solution for this is to learn all of the connectors via a hypernetwork, right? You can think of the connectors as representations. So you have n times m connectors. That means you have n times m representations over a large space. That is the space of all the weights of the connectors. So what we do is we train a hypernetwork that jointly learns to predict the weights of all n times m connectors. Or in other words, we learn the distribution of the weights of connectors across n times m settings, right? Well, what are hypernetworks? So hypernetworks, for those of you familiar with the image generation domain in diffusion models, you might know them, but hypernetworks are not super mainstream right now. So a hypernetwork is a neural network that generates the weights of another neural network. Very meta, but that is precisely the idea. This was inspired from the genotype and phenotype abstraction in nature. So all of us have certain genotypes, and they give rise to physical features that are phenotypes. So the genotype is the hypernetwork, and the parameters of the main network become the phenotype, right? Hypernetworks have had vastly interesting applications. For example, you can predict full parametric spaces of large models. So the figure here comes from a paper called Graph Hypernetwork 2, GHN2, by Boris Knadzev, who is also a co-author on this paper, on our paper. where they learn a computational graph of a neural network and use a hypernetwork, which is really a graph neural network, to predict the weights of every operand in the computational graph. They basically predict weights of full-scale ImageNet models. Another application is to predict small parameter spaces to condition other models. This is something that's very popular currently in the hypernetwork space, especially in the image diffusion space. Another very interesting work is by Sun. It was released this year, and it's called Hypersteer, where given a certain prompt, you would generate steering vectors of a language model, and that would shape the generation better than better than you would obtain when you just gave the reference prompt directly to the LLM. It's basically adding some secret sauce or some secret specialized knowledge per prompt. And I think that such applications will see large adoption in the future. So coming to our case, we want to predict full parameter spaces. And to be more specific, we want to predict the parameters of the connector, the one trainable module between your modality specific modules in your multimodal system. So let's think of a simple abstraction about this, a very simple mathematical one. We want to map an input I to a function fi, right? Here I is the index of the uni-modal model pair. If you remember, we had n times m pairs. And so if you think of pair, if in the image model space, you think of the jth model, and in the text model space, you think of the kth model, then I is the index of the pair j comma k. It's like a tuple, if you wish to model it so. Fi then becomes the connector for the ith pair. Mi becomes the dimensionality of modality 1 features, and mi2 becomes the dimensionality of modality 2 features, so that the connector does its job by projecting from one modality space to the other. Now, if you use I as a condition to a hypernetwork as hi, then you can generate theta I from hi, which are parameters of the function, and you can model that as a composition of a function g under parameters theta I. So fi becomes g of an input given the parameters theta I. So this is effectively what a hypernetwork does. It has a fairly complex looking architecture, but it's not that complex in practice, really. The idea is that we want to be able to predict variable dimension parameter spaces. So if we have, say, an MLP and it has 3 layers, then what we want to do is predict n times m MLPs, which are each of 3 layers, for example, right? And to store the layers, we use a lookup table, an embedding lookup table called EH, and the omega in the subscript is just denotes the weights. So EH is used to look up the layers to predict. WH looks up the model combination, the index of the uni-modal model pair to predict. And once we add CK to E1, E2, and E3, we get a conditioned input across the specific setting of the connector and for the specific layer configuration of the connector. And then we just decode them. We decode them to the largest parameter space that is available in the MLP. In this case, the largest parameter space in the MLP is D2 times D3. And what we do then is just slice them to get the precise shapes. The slicing seems rather crude, but it works fairly well in practice because it basically guides the parameter decoder to learn very compressed representations of the variable sized MLPs. Our main this is our main training scheme, which synergizes very well with what we want to do, which is search quickly and accurately. So the idea is that the hypernetwork can relate similar uni-modal models. And we use this factor as a basis for data efficiency. So the main idea is to never repeat data, The idea is to repeat model pairs to add representative knowledge of the connector weights. So as you can see in the diagram, if we imagine a timeline where we get data batches, that are the ones labeled 1 to 9 in blue, what we do is we also create a mini batch of model pairs that are the ones in red. So for data batch 1, we apply model batch 1 and then use those embeddings to update the hypernetwork. For data batch 2, we apply model batch 2. For 3, 3, 4, 4. But then for data batch 5, we cycle back to model mini batch 1, right? So what this does is that this effectively lowers the amount of data that the hypernetwork sees from each model pair. If you would run grid search and then train every single model pair independently, then you would see the entire data set. Or if you say you train it for 5 epochs, then you would see 5 times the number of data set samples per model pair. But here, we don't. What really adds our data efficiency is this idea to effectively lower the amount of data seen per pair so that the hypernetwork can learn to relate the functional similarity between uni-modal models and still be able to take a step towards a general local minima every single time. Coming to our experiments are rather simple. What we want to do is evaluate our hypernetwork connector prediction scheme on two popular multimodal settings. The first is clip-style VLMs, which use the contrastive info NC loss and two encoders, an image encoder and a text encoder. The second scheme is the lava-inspired scheme that comes from multimodal LLMs, right? So the idea over there is that we would, one second, I'm just getting, yeah. So the idea there is that you have an image encoder that projects, that outputs patch-wise features, and the patch-wise features are projected to the LLM's embedding space, and then you train only the connector with the causal modeling loss. For both settings, we have different amounts of total model pairs. So for the VLMs, we have 9 times 3, which is 9 image encoders and 3 text encoders, total 27 pairs. And for the second setting, we have 3 cross 3, 3 image encoders, 3 LLMs. And to basically evaluate our hypernetwork on outputting various connector parameter scales, we change the connectors from a linear layer, 1-layer MLP, and a 2-layer MLP. So for VLMs, the basic idea is to have a zoo of n pre-trained image encoders, a zoo of m pre-trained text encoders, embed an image across the image encoders to get a vector of dimension d per encoder. So you get n times d, a tensor. Similarly, for the text, you get m times d star. And then we use a connector to map from dimension d star to d. And the weights of that connector are generated by the hypernetwork. And so you basically backpropagate the clip loss all the way to the hypernetwork, but never to the pre-trained encoders. For MLLMs, this is very similar again. We have an image encoder, and an image encoder will output embeddings which go to various modality connectors because we have various LLMs. This is a 1 cross 3 setting. So if you have one image encoder and 3 LLMs, one would require 3 connectors. The connectors would then map image features to the LLM embedding space. These features are concatenated, sent to the LLMs, and then the LLM is trained on a language modeling loss. But the loss is only backpropagated to the hypernetwork and not to anything else. So what we do is we first experiment at a small scale. We want to see how this performs at a smaller scale so that it could guide our implementation on a larger scale. So the idea here is to use only 3 pairs. So we have 3 image encoders and 1 text encoder. And we want to find the best clip-like model we can. The connector here is a one layer MLP, and the evaluation task is image classification. I'm sure you all know how clip is evaluated on image classification, so I guess we can skip that. As you can notice in the graph, when we train the hypernetwork or our method Hyma, we find that it is really, really flop efficient. In fact, it is 4.4 times more flop efficient than grid search. So in the graph, every point that you can see is an epoch of training. So there are 10 epochs. We keep them same for both grid search and our method Hyma. And we find that Hyma uses fewer flops. This is very interesting, and this is mainly because of how our training pipeline is set up. As you can recall, in our data efficient setting, what we do not require is to show the hypernetwork every single sample from every single model. And this setup really helps our network become efficient and perform actually equivalent to grid search. As you can see at the highest point in ImageNet, both methods achieve an accuracy of 27, but Hyma is slightly cheaper than training only one pair, but a lot cheaper than training all of them. On a large scale, across all of our models on 9x3, we now define a different way to measure the accuracy of Hyma. What we do know is that grid search is the ground truth. If we would pair every single model with grid search, that is really how every single model would perform and would be ranked. So what we do is we look at the ranking that Hyma generates in its process of searching for the best connectors and match it with the ranking predicted by grid search. We do this via the normalized discounted cumulative gain at K metric and also the Spearman's correlation metric, that is rho. And we find that for all of our tasks across all of our connectors, Hyma matches grid search very, very well. So the previous experiment shows you that Hyma is cheaper than grid search. And this experiment shows you that Hyma matches the ranking of grid search. So it highly reflects the true ranking and the true nature of the models that you would get. So this, in fact, does check off the box that we search cheaply and accurately. And at the n times m equals 27 scale, we find that the average cost of search via Hyma is 10 times cheaper than grid search. However, the rankings are almost exact. Especially the top 5 ranks, the top 5 to 10 ranks are never different. Now, what's interesting is that, well, we might be cheating here, right? We have this very efficient training setup, which doesn't show the hypernetwork all of the data and applies this efficient model batching scheme, right? So no wonder we're efficient. Let's try and put Hyma and grid search on an equal footing by first trying to prune the number of models that we won't need. So ideally, we're only interested in the best model. We're trying to search quickly, cheaply, and accurately. So we're only interested in the best model. Let's do grid search. And at every 2 epochs, every 1/5 of the full training run, we can prune the models that lie below median performance. And so this way, we'll have more flops to do grid search. Well, what this does is basically give you a worse checkpoint for the connector. And from this, we realize that the connector really benefits from training for longer and from a higher flop consumption. But this is not the case for Hyma, right? So what we do is we use the top nm equals 12 connectors. And for each connector, we plot the difference in the performance, or we report the difference in performance across all of our tasks and all of our connectors under this pruned auto pair GS scheme. As you can see in the image classification setting, we're as high as 11%, right? In image text matching, we're as high as 11 points in recall at 5. And this goes to show that grid search doesn't effectively arrive at a good enough minima while operating within Hyma's flop budget, right? So when we use grid search in Hyma's flop budget and prune in order to raise the effective cost, we still don't get a good enough connector that Hyma gives us. Putting it on an equal footing, what we do is we reduce the amount of data that we show to grid search, right? Because in our training scheme, this is what we leverage. We use the relationships between models to not require as much data per model. So we show grid search the same fraction of data per model pair that we do in Hyma. What this leads is, again, a worse connector checkpoint. The connector predicted by Hyma performs much better than the connector predicted by constrained grid search, and constrained indicates that this is on an equal footing in terms of data samples. Now, coming to our second setting, in MLLMs, we again find the same trend. This time, however, the efficiency gain is slightly lower, that is 3x. One thing that we have to note here is that in the MLLM setting, the Hyma ranking does not match the ground truth grid search ranking. However, it does match performance. So as you can see in the left chart for the image captioning perplexity on MS Coco, grid search finds that the best model to stitch with our reference image encoder is Pythia, but Hyma finds that to be Quen. However, the best performances the best performance for Quen and for Pythia is the same, right? So here we find that Hyma doesn't match grid search, but it does match the performance of it, and it is still 3x cheaper. On full scale, the normalized discounted cumulative gain and Spearman row suffer. Again, it's because Hyma does not match grid search, and it only does so for larger connectors, so for MLP1 and MLP2. So while the net efficiency gain is still large, the main point is that the MLLM setting is less suitable for Hyma overall. And what we investigate here is that this is likely due to the functional difference in how the multi-modal system is created. So in VLMs, we have output to output stitching, right? The image encoder output is stitched to the text encoder output is stitched to the image encoder output, and the connector is trained in a confined local embedding space. But the fusion operation in MLLMs, that is the concatenation of the projected patch-wise image features to the LLM embeddings, that's an output to input stitching. And so this functional form, we believe, is less suitable for Hyma, as it basically allows for worse off training and does not reflect the true performance. So as I mentioned, worse off training. The main problem that we encountered with Hyma is sensitive training, especially with vastly different models. So when we train at higher batch size, we have a bit of an unstable training, and we also find that Hyma training is very learning rate sensitive. We also find that if our model pool that we train Hyma on is very diverse and very functionally divergent, then we find that we have NAN loss values. So what we did was we included max VITs with a pool of EVAs and VITs and DEITs, and we found NAN loss values. This is basically because max VITs contain convolutions in their attention and in their ML feed forward modules, and they functionally are very different from VITs. Their embedding spaces are very different from VITs, and it likely does not allow the hypernetwork to learn relationships in order to work well in our model mini batch setting. So this inspires us to solve the unstable hypernetwork training problem. And with that, hypernetworks can become more applicable and ubiquitous in adoption across everywhere. And what's also interesting is to experiment with more modalities, such as audio or videos, as there are models like audio clip and audio LLMs. So that's also very appealing to us. The main takeaway is that instead of training many small networks at maximal compute utilization, which would be expensive, you can train one large network to predict the small ones, and that would be more efficient search. The idea mainly is to reduce the amount of flops that you spend for search and to maximize the amount of flops that you would use for downstream adaptation of the searched best model, which is precisely what Hyma solves. However, there is a notable point that Hyma solves this case much better in the setting for VLMs and worse for the settings for MLLMs. Also, training of large hypernetworks is hard. Something that helped us is reducing beta 2 of Adam, but this is still an open problem that we are very excited to receive any input for. Thank you.
So yeah, I think that is pretty much it. We can jump over to the questions, right? So yeah,
Please feel free to ask any questions.
yes.